Welcome to the Step 1 primer video on pharmacokinetics. Now this is a very high yield topic for Step 1, and this video probably bears watching several times. At the very least, make sure you know the 4 pharmacokinetic equations and how to use them. Hope you enjoy the video.
It's time for that 3-question warm-up. Let's get going. First question here, what are the symptoms of excess parasympathetic activity? So remember, basically these make you leaky everywhere. Remember there's a mnemonic dumbbells, which stands for D, diarrhea, U is for urination, M is for meiosis, B is for bronchospasm, the other B is going to be for bradycardia, and then there's an excitation of skeletal muscles and CNS. Now technically this is more of a cholinergic effect, which is not exactly a parasympathetic effect, but you can still remember that one. Lacrimation, so you're drooling everywhere and crying everywhere. Sweating goes along, leaky again. And again, the sweating is technically a cholinergic effect, not exactly a parasympathetic effect here. And then salivation is another one, so you're drooling again more. All this leaky activity is what's going to prompt you to remember this. Next, we have atropine is not effective in reversal of organophosphate poisoning. What drug would best help this patient? So this is pralidoxime. So pralidoxime is going to actually regenerate acetylcholinesterase. Next, what are the symptoms of inhibiting parasympathetic activity? So remember, this is you're dry as a bone, so you have decreased secretions and decreased salivation, so anti-leaky is basically what you got to remember here. You're hot as a hare, so that's increased temperature, red as a beet, peripheral vasodilation, blind as a bat is mydriasis and a cycloplegia. Mad as a hatter, that's going to be agitation and delirium, and then bloated as a toad, that's going to be constipation and urinary retention. All right, that's it for the warm-up. Let's get to that lecture now.
In this video, we're going to talk about pharmacokinetics and enzyme kinetics, which are probably 2 of the biggest reasons that students hate studying pharmacology. It's not necessarily clinically relevant, but this is the type of thing that test makers love to test you on. Pharmacokinetic principles are very, very high yield. They're probably a lot higher yield than a lot of the clinical, disease-specific stuff that you'd like to study. So make sure you know everything in this video and in the next video. Now, I'm going to spend most of my time focusing on what's most important for your exam, but don't neglect this stuff. It's very, very high yield. So let's start off with enzyme kinetics. Again, this is at least a 4-star topic, maybe 5 stars. You should expect at least 1 question on enzyme kinetics and Km and Vmax. We've had students come back after step 1 and tell us you need to know Km and Vmax like the back of your hand. So let's start out with something called Michaelis-Menten kinetics. Say you have an enzyme that catalyzes some reaction, and you mix some of that enzyme with the substrate, which is S. And you measure the velocity of that reaction. So this graph shows you how the reaction velocity changes as the concentration of substrate changes. So the x-axis is the concentration of substrate, and the y-axis is the reaction velocity. So the first thing to notice is that down here, as the substrate concentration increases, the reaction velocity increases. More substrate leads to faster reactions. We call this first-order velocity, where the reaction velocity is directly proportional to the concentration of substrate. But as you continue to add more and more substrate, eventually you're going to saturate the enzyme, right? Now once that enzyme gets saturated, you can't make the reaction go any faster no matter how much substrate you add. So up here, the enzyme is completely saturated and the reaction velocity reaches a plateau. We call this zero-order velocity, or zero-order kinetics, because the velocity is completely independent of the substrate concentration. It doesn't matter if you've got 1,000 particles of substrate or 1,000,000 particles. If there are only enough enzyme binding sites for 100 particles, the velocity of the reaction is going to be the same. We call this maximum reaction velocity Vmax. That's the maximum velocity that the reaction can achieve. If you wanted to speed up the reaction, how would you do it? Well, the enzyme is saturated, so the only way to speed things up would be to add more enzyme, right? If you add more enzyme, you have more binding sites, and that shifts the whole graph up some, and Vmax is a little higher. So ultimately, Vmax is proportional to the amount of enzyme that's available. Now, what about Km? What is Km? Km is called the Michaelis constant, but that's not really important. What's important is that you know that Km is a substrate concentration. Specifically, it's the concentration of the substrate that gets your reaction to half of Vmax. It's the amount of substrate required for the enzyme to achieve half of the maximum velocity that that enzyme can achieve. So Km is a substrate concentration. If you look at this graph, you would say that this is Vmax, and when half of Vmax is here, halfway between Vmax and 0, then wherever that half Vmax is, you follow it out horizontally to intersect the graph, then drop down vertically to the x-axis, and whatever that concentration is, that's Km. So Km is the substrate concentration at 1/2 of Vmax. It's really pretty straightforward. Now, Km reflects the affinity of the enzyme for its substrate. If the enzyme has higher affinity for the substrate, the slope of the graph will be steeper. You're going to get to Vmax much faster, so Km will be lower. So a lower Km means that the enzyme has higher affinity for the substrate. It doesn't take as much substrate to get to half Vmax. So far so good, I hope. So let's look at this in a different way. This is called a Lineweaver-Burk plot. It's the same data, but it's plotted on different axes. In a Lineweaver-Burk plot, the x-axis is 1 over S, 1 over the substrate concentration, and the y-axis is 1 over V, or 1 over the reaction velocity. What that does is straighten out the curve. Now, the 3 points you have to know about this, and I really think you just have to memorize it because there's not a great way to reason it out. The 3 points to memorize are the slope of this graph, the x-intercept, and the y-intercept. So the slope of a Lineweaver-Burk plot is Km over Vmax. The x-intercept is the point where the graph crosses the x-axis, and that's 1 over minus Km. And then the y-intercept is 1 over Vmax. Now watch this. If you add more enzyme, that's going to increase Vmax, right? That's going to flatten this graph out some, and if Vmax is higher, the slope is lower, right? But Km hasn't changed because Km is related to the enzyme's affinity for the substrate, right? Not the enzyme concentration. Increasing the y-intercept means you have a lower Vmax because it's inversely proportional. And then the further to the right the x-intercept is, the greater the Km. So be able to identify those two things. Now let's think about what happens when you add a competitive or a non-competitive antagonist or inhibitor. A competitive inhibitor is a substance that resembles the substrate so it can bind to the active site of the enzyme and compete for the active site. So if you give enough substrate, you can dilute that competitive inhibitor out, so it's basically irrelevant. So competitive inhibitors can be overcome by increasing the amount of substrate so they can be diluted out, so to speak. And then a non-competitive inhibitor is a substance that instead of binding to the active site, they generally bind to some other site of the enzyme and they render the enzyme inactive. So these tend to be irreversible, so sometimes we call them irreversible antagonists. But the important thing here is that you can't dilute them out by adding more substrate. So how do these inhibitors affect enzyme kinetics? Well, a competitive inhibitor does not affect Vmax. You can still achieve that same maximum velocity eventually if you give enough substrate. So with a competitive inhibitor, the curve is basically shifted to the right. But again, Vmax doesn't change. Then with a non-competitive inhibitor, you can't overcome the inhibition by giving more substrate. So at some point, you're going to saturate the available enzyme and hit that zero order velocity. And what you'll find is that when you reach that plateau, the Vmax is lower. So non-competitive inhibition will decrease Vmax, but it doesn't change Km. Now, what does that look like on the Lineweaver-Burk plot? Well, here the yellow line represents the uninhibited enzyme. So when you put a competitive inhibitor into the system, does that affect the Vmax? Vmax we said was related to enzyme concentration. So that doesn't change. So a competitive inhibitor does not affect Vmax, which means that the y-intercept doesn't change. But it does change your x-intercept, which is changing Km. A competitive inhibitor is going to increase Km because Km is the substrate concentration at half Vmax. It takes more substrate to get to half Vmax with a competitive inhibitor on board. Then what about a non-competitive inhibitor? A non-competitive inhibitor is basically taking enzyme binding sites out of commission, right? And it's going to decrease the maximum reaction velocity, or Vmax. So a non-competitive inhibitor doesn't change Km at all, but it does decrease Vmax. So with a non-competitive inhibitor, the x-intercept doesn't change, but the y-intercept is going up. What happens when you increase your y-intercept? You're decreasing your Vmax. So a non-competitive inhibitor is going to decrease your Vmax. Now we're going to look at competitive and non-competitive inhibitors again in the next video when we talk about efficacy and potency. So let's take a second and practice these. Look at number 4 and number 5 in your study guide, and I want you to pause the video and try to label these, and then we'll talk through the answers. So in question number 4 on the Michaelis-Menten graph, A is Vmax, B is 1/2 Vmax, and then C is Km, which is the concentration of substrate needed to achieve 1/2 Vmax. D is indicating the region of first order velocity, and then E is indicating the region of zero order velocity. And on the Lineweaver-Burk plot, F is 1 over minus Km, and G is 1 over Vmax. So those two are just things you're probably going to have to memorize. Now, for question number 5 in your study guide, A is a competitive inhibitor where you're increasing Km, but Vmax is unchanged. And B is a non-competitive inhibitor where Vmax is decreased. Then on the Lineweaver-Burke plot, C is a non-competitive inhibitor where Vmax is lower, so the y-intercept is moved up, and D is a competitive inhibitor where you're changing Km. Next, we're going to talk about all sorts of calculations that are related to pharmacokinetics. Now, pharmacokinetics is another hugely high-yield topic. I know it can be a pretty intimidating topic. There are a bunch of different equations, and you got to figure out how to use them. Some of this is just stuff you're going to have to memorize and then be able to plug the numbers into the equations. Fortunately, there are only 4 pharmacokinetic equations you need to know, only 4. The questions you're going to see on your exam shouldn't be too difficult if you know those 4 equations. So number 6 in your study guide has space for you to write down these 4 equations as we go through them. The first equation is the volume of distribution equals the amount of drug given in the IV form divided by the concentration of the drug in plasma. And we say IV form because basically we're factoring out bioavailability. When you give a drug IV, it's 100% bioavailable. Volume of distribution is the amount of drug that's given divided by the plasma concentration of the drug. The second equation deals with clearance. Clearance is the rate of elimination of a drug divided by the plasma drug concentration. Clearance is also equal to 0.7 times the volume of distribution divided by the half-life of the drug. And that's probably the equation you should memorize. Another way that you can remember that is that the clearance is K times the volume of distribution. K is the elimination constant. And these 2 equations together tell us that K is 0.7 divided by the half-life. So clearance is equal to the elimination constant times the volume of distribution, where the elimination constant is 0.7 divided by the half-life. The third equation is the loading dose. Loading dose is equal to the concentration at steady state times the volume of distribution. Now what's the concentration at steady state? That's your desired concentration, your target concentration. You're giving a drug and you know you have to get it up to a certain plasma concentration where it's going to have the desired effect. So to determine the loading dose, you need to decide what your desired concentration is and then multiply it times the volume of distribution. Then the fourth equation is the equation for maintenance dose. Once you've got that drug up to that desired concentration, you have to keep giving a dose every day or every 8 hours or whatever it might be in order to maintain that steady state concentration. So the equation for the maintenance dose is the steady state concentration times the clearance. It makes no difference how big the patient is or what the volume of distribution is. Maintenance dose is not determined by the volume of distribution. It's determined entirely by the clearance. So those are the 4 equations you definitely need to know for your test. Volume of distribution, clearance, loading dose, and maintenance dose. If you know those, you should be in good shape. We're going to practice using those equations, plugging in the numbers and such, in just a moment in the end of session quiz. The best way to show you how to use these equations is just to practice using them. But one thing I want to say about these equations, it's a perfect example of what we call a marker board topic. So what does that mean? Well, when you go in to take step 1, you go into the testing center, after you've checked in, you sit down at the computer station to take the test, they're going to give you a marker board and a dry erase marker. And the marker board is just a couple of sheets of paper that have been laminated. We recommend that the first thing you do as soon as that first block starts is to spend a couple minutes sort of regurgitating a few equations and facts down, put that down on the marker board. That's stuff that's going to help you move more quickly as you go through the test. So one of the things that we recommend that you write down on your marker board is these 4 pharmacokinetic equations. So if you can put down those 4 equations on your marker board right up front, then when you come across one of these questions later on, you don't have to panic. You just start plugging in the numbers. Now we're going to talk about some other marker board topics throughout part 2 of the course. But these 4 equations are a great marker board topic. You still have to memorize them up front though. Then another thing to be aware of when you're calculating loading dose and maintenance dose is bioavailability. Now bioavailability takes into account the fact that when you take some drugs orally, all the drug doesn't actually get into the blood. Most oral drugs have bioavailability less than 100%. So sometimes you'll see an equation that says loading dose equals concentration steady state times the volume of distribution divided by F, where F is the bioavailability. But the good news is that we've never heard of students having questions that ask you to adjust for bioavailability. So the question will either specifically say it's 100% bioavailable in oral form, or they're going to say that the drug was given IV. So I think it's pretty safe to just forget about F, forget about bioavailability when you're memorizing these equations. I also want to say a quick word about half-life. Half-life is the amount of time it takes to eliminate half of the drug that's in your body. And if you're infusing a drug at a constant rate, that drug is going to reach about 94% of the steady state concentration in approximately 4 half-lives. That's a number you want to know. 94% after 4 half-lives. So if you're infusing that drug constantly, it's going to hit 94% of the steady state at 4 half-lives of the drug. But it's also going to be eliminated in the same way. So when you stop the infusion, you let a patient sit for 4 half-lives, about 94% will be eliminated during that time also. So it works both ways. I would know those numbers. After 1 half-life, obviously you've eliminated 50% of the drug. At 2 half-lives, you've taken out another 25%, so now you've eliminated 75% of the starting amount. At 3 half-lives, you've eliminated 87.5%, and at 4 half-lives, you've eliminated 94%. And those numbers work the other way too. So if you're giving a drug, after 1 half-life, you've achieved 50% of the steady state concentration. After 2 half-lives, you've achieved 75% of steady state, and on up to 94% after 4 half-lives. So again, those are numbers you definitely want to know. So now we're ready to tackle the end of session quiz, which is going to focus entirely on doing calculations with our 4 pharmacokinetic equations. So all these questions in the quiz deal with this situation. A 60-kilogram man with status asthmaticus is being given an IV infusion of drug X at 60 milligrams per hour. The clearance of drug X is 2 liters per hour, and the volume of distribution is approximately 0.5 liters per kilogram. 48 hours after administration has begun, the asthma attack is under control. At this time, the concentration of drug X in his plasma is 20 milligrams per liter. So go ahead and try to answer those 5 quiz questions, and then we'll work through them together. All right, the first question is, what's the half-life of drug X in this patient? So you start with the equation for clearance. Clearance equals 0.7 times the volume of distribution divided by the half-life. Then you switch it around, and you get the half-life equals 0.7 times the volume of distribution divided by clearance. So to figure out the answer, you need the volume of distribution, and you need the clearance. Well, the clearance was given in the question. So the clearance of the drug X is 2 liters per hour. Then the volume of distribution is kind of given. It says the volume of distribution is 0.5 liters per kilogram, but liters per kilogram is not a unit for volume. You have to pay attention to your units in these problems. Volume is just liters, not liters per kilogram. So you need to take into account how many kilograms the patient is. So if this patient is 60 kilograms, the volume of distribution for this drug in this patient is 0.5 times 60, which gives you 30 liters. So the volume of distribution here is 30 liters. You multiply that by 0.7, and you divide by your clearance, which is 2, and you get 10.5. So the half-life here is 10.5 hours. Next, what loading dose could have been used to reach the target concentration of 20 milligrams per liter? So in order to calculate your loading dose, you take the target concentration of 20 milligrams per liter and multiply it by the volume of distribution, which you just found was 30 liters, and you get a loading dose of 600 milligrams. Next, if the patient begins to show signs of toxicity and the target dose or target concentration is decreased to 10 milligrams per liter, what would you do to get to this level? So basically, you're cutting the target concentration in half. So how do we get to the new level? Well, you stop the infusion for 1 half-life. That's the meaning of half-life. You stop the infusion for 1 half-life, which is 10.5 hours, and then your concentration is going to be decreased by half. Next, assuming 100% bioavailability, and again, they're either going to tell you that the drug is 100% bioavailable, or they're going to say the drug is given IV. And if it's an IV drug, you just assume it's 100% bioavailable. So assuming 100% bioavailability, what oral dose of drug X would be necessary to maintain the new target level? So we're looking for maintenance dose here. Maintenance dose is equal to the concentration at steady state times clearance. Our new concentration at steady state is 10. They gave us the clearance in the question. It's 2 liters per hour. So the maintenance dose is 20 milligrams per hour. And the last one. If the patient has kidney disease and the clearance is reduced to 1 liter per hour, but volume of distribution is unchanged, what effect will this have on the loading dose and the maintenance dose? So the loading dose is based upon the volume of distribution. We're told in this question that the volume of distribution is unchanged. So in this case, the loading dose doesn't change. But the maintenance dose is going to be decreased because of the reduced clearance. So you have to decrease the maintenance dose, but the loading dose doesn't change in this example. All right, that's it for pharmacokinetics. I'll see you next time.